now is to construct the Lebesgue integral. We will take limits of step functions, but not the uniform limit. If you take the uniform limit, as we saw in the previous video, we recover the Riemann integral for a subclass of functions. We will take a different sort of limit and define the integral using this limiting process. So essentially, we are going to study monotone sequences of step functions. But before we do that, I want you to think of an example of a sequence of Riemann integrable functions, in fact continuous functions. I want you to think of a sequence of continuous functions defined on some AB whose pointwise limit is not Riemann integrable. It is not that hard to come up with many such examples. Please do that now. The goal of the Lebesgue theory is to construct an integral which behaves very nicely with respect to limits. Of course, in general, you cannot expect with no additional condition on the type of convergence to for the limiting function to be both integrable and the limit of the integrals equal to the integral of the limit. That's too much to expect, but the resultant theory that we develop will be much better than the standard Riemann integration theory, where you need uniform convergence to interchange limit and integral. It will be better than that. So what we are going to do is we are going to now consider step functions, but for the construction it will actually help if we now define step functions on the whole of the real line. So the definition is as follows. So we start with any interval. Let I be any interval. Open, closed, unbounded, the whole of R, I don't really care. And let S from I to R be a function such that for some closed interval, AB subset of I, we have number one, S restricted to AB is a step function. In other words, we can find a partition of this closed interval AB such that on the open intervals determined by the partition, the function S is constant. Number two, S is identically 0 on I minus AB. So outside this closed interval AB, the step function is actually just 0. So this is called a general step function. This is slightly a larger class of functions than the type of step functions we considered in the last video when we wanted to define the Riemann integral in terms of the step functions. Okay, so now that we have this, we can define integral of A to B of the step, not integral of this A to B, integral of I of the step function to be nothing but integral A to B of the step function S. Because S restricted to AB is a step function in the usual sense that we have seen in the last video, we can define this integral. However, there is one slight issue which is not that major, and as usual I'm going to leave it as an exercise to you. Show that the above is well defined. The issue that can arise is there could be more than one interval closed AB outside which S is identically 0 and S restricted to AB is a step function. That's very easy to see that there can be more than one interval. I want you to check that if you choose another CD, which is a subset of I, such that S restricted to CD is actually going to be a step function and S is identically 0 on I minus CD, that is conditions 1 and 2 satisfied for the closed interval CD also, then you have two possible definitions. You have to show that both are equal. So you will have to show that integral A to B S is integral C to D S, and that's not too hard, that's rather easy. And let's call this first part of this exercise. Second part, show that integral of s plus t over I is integral s over I plus integral t over I, and integral over I of cs is c times integral of I, integral of s over I. And if s is less than or equal to t on I, then integral of I s is less than or equal to integral of I t. All the basic properties of the integral continue to hold true for these more general types of integrals defined for general step functions. And also we have this other property that you are no doubt familiar with. If you have some interval and you break it up into smaller intervals such that each piece intersects only at the endpoints, it could be half open, half closed, you just break it up in some way. That is, if I is union over, let's say, j running from 1 to p, a j b j, okay, where a j b j are pairwise disjoint except for possibly endpoints, that is, no two intervals have an interior point in common, then if s from I to r is a general step function, then integral over I s is actually summation over j integral aj to bj of s. And this also follows more or less directly from the very definition of the integral of a step function. Now notice that if you had defined the integral of step functions via the Riemann integral, everything I have written down in this exercise is trivial. You don't need to do anything to prove it. But if you take the definition of the integral of a step function not using the Riemann integral, but by the way we have defined it in the last video, there is a little bit of work to be done, but it's minimal. Okay, so with all this said, we can come to the main theorem that will allow us to define the Lebesgue integral. We are going to consider sequences of functions, sequences of step functions that are monotone almost everywhere. So let me recall that a subset E of R is said to be a set of measure 0, if we can find for each epsilon greater than 0 an open cover of E such that the sums of the lengths we can, for each epsilon greater than 0, an open cover of E consisting, let me just make the definition slightly easier, open cover of E comprising intervals whose sum of lengths is less than epsilon. So no matter what small epsilon you choose, you can always find an open cover of this interval. The sum of the lengths of these intervals should be less than epsilon. Okay. Now we studied this sets of measure 0 in quite some detail when we studied the Riemann-Lebesgue theorem, which gives a precise condition for when a function is Riemann integrable. If you have not come across this notion of sets of measure 0, that is, if you have not taken real analysis 1, please go through the lecture notes provided at the very first week. There in the chapter on Riemann integration, we go at this in great detail, why these sets of measure 0 are important and what they have to do with integral. Basically, these are sets that are negligible in some sense. Okay, so just for sake of clarity, as an example, you can show that any finite or countable set is a set of measure 0. And any interval of positive length, that is any interval which has an interior point, will not be a set of measure 0. If you can solve these two now, you are good to go for what is to come. Okay, now one other definition: a property is said to hold almost everywhere. As mathematicians are very lazy, almost surely nobody is going to write this almost everywhere in full detail. We will just abbreviate it to AE. A property is said to hold almost everywhere if the property is true. Property holds outside a set of measure 0. Outside a set of measure 0. The property that we are interested in this particular video is sequences. So we have a sequence. Of step functions that almost everywhere increase to a function f. Okay, that increase or decrease. That is, these are functions that are monotone except for a small negligible set. Outside of that small negligible set, these functions are either increasing or decreasing to a given function. We are going to consider a sequence of such functions, and if those sequence of functions satisfy some conditions, then actually you can interchange limit and integral. This is the starting point of the Lebesgue theory. We will denote this by Fn increasing to f AE or Fn decreasing to f AE. We will use this upward slanting arrow for increasing and downward slanting arrow for decreasing. So the precise theorem, which is the main theorem of this particular video and the theorem that is going to allow us to define the Lebesgue integral, is as follows. Let Sn be a decreasing sequence of general step functions on I such that these are non-negative. Okay, a decreasing sequence of non-negative, that's crucial, non-negative general step functions on I such that Sn decreases to 0 almost everywhere. Okay, so we are considering functions which are decreasing, number one, and this decreasing is everywhere, okay, not just almost everywhere, and these Sn's are decreasing to 0 almost everywhere. Then integral over I of Sn converges to 0. Inside, if you notice the integrand, the limit of this is of course 0 because these sequences are decreasing almost everywhere to 0. What is essentially happening is, if the limit were inside, you will get 0. That limit can be taken outside. That's essentially what is being asserted. So at least for these very nice sequence of non-negative step functions defined on the interval I, we can interchange the limit and the integral, and we are going to use this as the starting point of our theory. Those who took Real Analysis 1 and studied the proof of the Riemann-Lebesgue theorem in some detail will find this proof very, very similar to the proof that we saw there. The ideas in this particular proof are typical of the proofs in analysis. You want to estimate this integral over I Sn, what is going to happen to that, and the goal, the way you estimate that is, you break up I into two pieces. In one piece you can control Sn, In the other piece, you don't have control over Sn, but you can control the size of that other piece. So what you essentially do is, since this function behaves well except on a set of measure 0, because we have decreasing to 0 almost everywhere, outside of the points where it is outside of the points where it is not decreasing from 0, the function can be made really small. And those points where it is failing to decrease to 0, it's actually a negligible set, because those points are only going to be a set of measure 0 by hypothesis. There you can control the size of the intervals, though you cannot control Sn there. Together will yield the result. So let's see the proof. Idea is to write I equal to A union B, where A and B are intervals A and B consist of finite union of intervals such that they have no interior point in common. Then we can use the last property of the integrals that I stated in the exercise. When you can break up I into a union of intervals, then there is some nice summation property. We will use that. They have no interior point in common. Okay. Then obviously you will have integral over I Sn is sort of integral over Sn A plus integral over Sn B. And each one of these will go to 0. Both this as well as this will go to 0 as n increases. That's the basic idea. That is, we can make both of these small. Both are small. Okay. So what are we going to do? Well, let A be subset of I be such that S1 is identically 0 on I minus AB. Outside of this closed interval AB, S1 is identically 0. Because Sns are decreasing, Sn is identically 0 on I minus AB. That is why we assume that Sns are globally decreasing and not just almost everywhere. It will make our life easy. Okay. Now each Sn is constant in some partition in the open intervals determined by some partition of AB. Note, this partition will depend on n. Okay, let Dn be the endpoints of such a partition. Endpoints of such a partition. Now, why we want to focus on the endpoints is because the way we defined a step function, we sort of said that we don't care what happens at the endpoints. It could take whatever value the function pleases. Okay, so we have really no control over the behavior of the functions Sn on the endpoints. But notice that Dn is finite. Therefore, the union of Dn as n runs from 1 to infinity, which we just called D, is a countable set. And is therefore a set of measure 0. Therefore, a set of measure 0. So we have isolated one set of bad points, those points where there is an endpoint of the interval of constancy of one of the step functions. All such endpoints of partitions we have put together in the set D, and that set is thankfully a small set because it's countable. Furthermore, we have a set set of measure 0, say E subset of AB, such that Sn decreases to 0, converges to 0 essentially on AB minus E. Outside of a set of measures 0, we already know that Sn converges to 0 because we are assuming Sn decreases to 0 almost everywhere. Okay. What we are going to do is we are going to define our bad set F to be D union E. So this F is the bad set. Outside of this bad set, we can completely control the behavior of the functions Sn by using the fact that Sn decreases to 0 there. How do we do that? Well, what you do is the following. Let X be an element of AB minus F. Oh, before that, simple observation, this is a set of measure 0. Union of set of measure 0, countable union of sets of measure 0 is also a set of measure 0. This is just a union of two sets of measure 0. The set D is a set of measure 0 because it's countable. E is a set of measure 0 by hypothesis. So let X be in an element in AB minus F. Okay. Then because Sn converges to 0 on X, because we are choosing X outside the bad set, we can find Nx, some natural number such that Snx is less than epsilon if n is greater than or equal to capital Nx. Okay, so we must write fix epsilon greater than 0, of course. So once you have fixed an epsilon, we can find a large enough natural number such that Snx is less than epsilon if n is greater than or equal to nx. Of course, this happens because Sn is decreasing to 0 on AB minus F. Okay. Notice that X is in the interior of the partition determined by the endpoints Dn. Right, we started off with the partition, all the endpoints we call Dn and put them separately in this set D, which we eventually put in the set F. This X is coming from AB minus F. That means in the partition determined by Dn, this X has got to be one of the interior points. It cannot be the endpoint of one of the subintervals. That means, this means Snx is less than Sny is less than epsilon in some interval that contains X. Okay, and this is true for all n greater than nx, greater than or equal to nx. Why is it true for all? Well, because the moment Snx is less than epsilon, then because it is constant on the subinterval, at some small piece it's going to be constant, and that constant is less than epsilon by hypothesis, but Sn's are decreasing. So if you take an even larger n, that constant can only decrease. Okay, so what happens is, I said that constant can decrease. It can happen that if you take a larger n, the function is no longer constant on the whole interval, but nevertheless it has to be less than Snx, which is constant. Okay, so apologies for that mistake, but I hope you catch my drift. Okay, now what you do is let b of x be this interval such that Sny is less than epsilon for all y in Bx n greater than or equal to nx. Okay. Now here is the crux. Since that other set, bad set F is a set of measure 0, we can cover F by a countable union of open intervals whose net length is less than epsilon. The set F is a set of measure 0, therefore we can find countably many open intervals whose union both cover F and whose net length is less than epsilon. Excellent. Now observe that AB is union of these Bx's as X ranges through AB minus F, and union these Fn's. Okay, union of Fn n equals 1 to infinity, where F is a subset of union n equal to 1 to infinity Fn, and summation of length of Fn is less than epsilon. These Fn's are open intervals whose net length is less than epsilon and they cover F. AB is compact. This means we can find some x1, x2 ... xp such that AB is a subset of union I equals 1 to p bxi and union some subcollection of these fj's. So I can say j running from 1 to some q of fj. Okay. So you can find a finite subcollection of these intervals bxi's and a finite subcollection of these fj's such that the union is going to be AB. Note, the Hein-Borel theorem will just give an subcover. Please think over why we can write this. Okay. It's direct from, it's one step away from Hein-Borel. This is not a direct conclusion of Hein-Borel theorem. Think about why you get this. Now we are going to define A and B. The original goal was to break up the integral into two pieces. On one piece A, we can control the behavior of Sn, and on the other piece Sn, on the other piece B, the set B can be made really small. That's the idea. And as you can guess, this part is going to be the small length intervals, and this part we have a good control of the functions Sn. Okay, so what are we going to do? Well, since the union j equal to 1 to q, fj is a set whose net length is less than epsilon, we have integral over b of Sn is less than or equal to m times epsilon, where m is the supremum of mod S1 of x, or rather I can just write it in shortcut notation as the norm, subnorm of S1, right? Since the function S1 is a step function which vanishes outside the interval AB, this is going to have a supremum, it's going to have a subnorm, m is that subnorm, and integral over b Sn is m epsilon. Okay, less than or equal to m epsilon. This is simply because the net length of these intervals fj has got to be less than epsilon. Excellent. Now we are going to deal with this integral of Sn over A. Right? But for all points x in A, we have Snx is less than epsilon if n is greater than maximum of nx1 comma nx2 comma nxp. Recall, how were these intervals bxi's chosen? Well, where did that definition go? We first chose this nx such that if n is greater than or equal to nx, snx is less than epsilon, and bx was the corresponding interval on which this Sn is constant, and therefore Snx will be less than epsilon for all y in Sny will be less than epsilon for all y in bx whenever n is greater than or equal to nx. This is the way this intervals bx and capital Nx were chosen. Now what I'm saying is, if you choose n to be larger than nx1 nxp, then the corresponding intervals bx1, bx2 bxp will cover ab minus f, and moreover whatever point x you choose from ab minus f, that is precisely not ab minus f, yes, correct, actually ab minus f, whatever point you choose from ab minus f, Snx will have to be less than epsilon if you choose n to be suitably large. Okay, so we have Snx less than epsilon, which means that integral of Sn over a is less than or equal to epsilon times b minus a, because the net length of the interval a will be less than b minus a. So what this shows is that integral of Sn over I is less than or equal to m epsilon plus epsilon b minus a. And by the k epsilon principle, which we are invoking after many lectures, we are done. What more elaborately, what we have shown is there exists capital N such that if n is greater than capital N, integral of I over s can be made less than epsilon. In other words, limit n going to infinity, this should be Sn. Limit n going to infinity, integral over I Sn is 0. So when you have a decreasing sequence of functions that almost everywhere decrease to 0, then what happens is the integral of those step functions will also converge to 0. Now, as an exercise, since this proof looks really complicated but the basic idea is simple, as an exercise, connect this to Dini's theorem. If you don't remember what Dini's theorem is, or you have not come across it, please Control F on the PDF notes for Real Analysis 1 and search Dini. There is an exercise where this has been done. Check the proof of that exercise. Hints are given. Solve that exercise and try to connect this particular theorem to Dini's theorem. That's a very interesting exercise to work out. So in the next video, we will define Riemann integrals for upper functions. These are functions that these are step functions. Upper functions are functions that arise as limits of step functions that are increasing almost everywhere. And the fact that this integral is sort of well defined will be a consequence of this theorem. So in the next video, we will define that. This is a course on real analysis, and you have just watched the video on monotone sequences of functions.